Hello and welcome back to our series of tutorials on how to use the scalable workflow execution engine Saasfee. In the last tutorial, we gave an introduction to the functional workflow language Cuneiform. This time around, we will encounter the other major component of Saasfee, the highway workflow scheduler for Hadoop Yarn. While Cuneiform provides a local execution mode that supports multi-threading and caching of partial results, processing data on a single machine simply won't cut it for some workflows that process huge amounts of data. Highway can interpret such data-intensive workflows and dispatch the tasks comprising the workflow to Hadoop Yarn, thereby harnessing the scalability and fault tolerance of Apache Hadoop. In this tutorial, we will have a closer look at a workflow for solving variant calling, an important step in the analysis of next-generation sequencing data. Note that this workflow, along with its required command line tools and its input data, is part of the set of advanced workflows included in the extended Saasfee installation. Let's get started by launching the Cuneiform editor from a terminal and opening the workflow file variantcall.cf. The problem solved by the workflow at hand is to determine and annotate variants in a genome based on the output of a sequencing machine. The variant calling workflow encompasses index-based string similarity search, probabilistic reasoning to cope with the noisy data, and multiple database lookups for finding related information. Scalability of this workflow is of major importance, as modern sequencing machines produce multiple terabytes of genomic data per week. Let's walk through the workflow step by step to get a feel for it. The task definition section consists of several tasks in Bash, each calling a tool with a command line interface. In the first step of the workflow, reads, the primary product of the sequencer, are aligned against the reference genome using the tool BWA. The resulting alignments are sorted using SumTools before variants are predicted with varscan and finally annotated with ANNOVAR. Note that each of these steps can be, and in practice often is, performed by other similar tools. The parameter section defines global workflow parameters, including the location of the input data. The workflow can be parallelized by partitioning the read set, the reference, for instance into chromosomes, or both. Here we use real read files from the 1000 Genomes project, the HG38 reference genome, which can be downloaded from UCSC to align against, and the ANNOVAR annotation database. While this particular instance of the workflow serves as an introductory example and thus only aligns two pairs of read files against two reference chromosomes, an actual productive instance of the workflow would process far more data. Next, the workflow definition section defines how intermediate results are computed from their inputs. All the data dependencies of the workflow are defined here. This is essentially a series of task applications, much like function applications in general-purpose programming languages. Finally, the query is the definition of what the workflow is supposed to produce. Up to the query, all statements were assignments or task definitions. Thus, the query is the only statement that actually triggers computation. Queries are lazy, so Cuneiform produces intermediate results only if they contribute to the query. Determining optimal toolchains and parameterization for a given experimental setting is a highly relevant and complex topic in many fields of science, including genomics. Providing flexibility in iterative workflow design and maintenance is thus very important for end users. To demonstrate how alternative tools and libraries can be managed in Cuneiform, we replace the alignment tool BWA in the workflow with another popular alignment tool called Bowtie2. In the variant calling workflow, look up the definition of the tasks BWA build and BWA align. We can write a pair of tasks Bowtie2 build and Bowtie2 align with otherwise identical signatures. In this workflow, the Bowtie2 task definitions are already given. Since the signature and data consumed and produced are the same, we can safely exchange BWA build and BWA align for Bowtie2 build and Bowtie2 align respectively. So let's do so. Let us save this workflow under a new name. Let us dispatch this workflow to Highway. But first, let's open a browser and display the web interfaces of Hadoop's Resource Manager and Distributed File System. Since Highway reads and writes data from and to Hadoop's distributed file system HDFS instead of the local file system, which makes sense for large amounts of data, we should make sure that the input data is actually present in HDFS. As we can see from the HDFS web interface, all of the input data is present. In a new terminal, we now enter highway -w variant call _bowtie2.cf -s bowtie2.json. Specifying a summary JSON file is helpful, as the output data generated by executing the workflow will be written into Highway's folder in the HDFS. Among other things, the summary file will give us a handle to the output data, which we can stage into the local file system after workflow terminus. While the workflow runs, we can track its progress in the web interface of Yarn's Resource Manager. We can also have a look at the HDFS file structure, where we can see that Highway is actively creating intermediate data. Let's wait for a couple of minutes for the workflow to terminate. Once the workflow has terminated, let us obtain its output data. For that purpose, Highway provides the stage command, which we can run to copy all of the workflow's output data from HDFS in a simple way. Repeatability of experiments is of utmost importance in science. Accordingly, Highway provides a comprehensive provenance trace that logs events and statistics at different levels of granularity. Let us have a look at the summary file. Aside from a handle to the output of the workflow, the summary file gives us links to several log files created during workflow execution. Let us obtain the stat log by running a manual HDFS command. The stat log is a full workflow trace, which is directly re-executable and therefore, together with the workflow input, a verifiable proof of the way an analysis result was derived. If we wish to re-execute the workflow with parameter settings identical to this particular run, we could dispatch the stat log to Highway for re-execution. The command for this would be highway -w, then the stat log -l log -s log.json. This brings us to the end of this session. We have learned how to alter a popular real-life workflow from computational genomics in Cuneiform and how to execute it on top of Hadoop using Highway. Note that just like Cuneiform has a local execution mode independent of Highway, Highway can also execute workflows written in other languages besides Cuneiform. In the next tutorial, we will have a look at how Highway is able to execute workflows exported from the popular bioinformatics workflow system Galaxy. Until then, thanks for your attention and see you soon.